All right, welcome everybody to today's installment of our lecture on image processing and so on. And here is what we are going to look into today. But first of all, we, I guess, better remind ourselves about what we have been doing last time. And that was, of course, we began our study of the idea of the Fourier transform. And last time we looked into where it comes from, why it was originally developed, and we already developed ourselves the notion of finite Fourier series. Well, today we will extend what we have been doing last time to the case of infinite Fourier series, and from there we will further generalize this to the Fourier transform. And let's see how that goes. But what was it that we did last time? Well, without actually carefully preparing you for that, I claimed that every L square function, that is, every function that is square integrable, and we focus on functions that map from the reals to the reals for the time being, we will generalize that later. Every such function f that takes a number, a real number, and produces another real number and is square integrable can be expressed like so. That is, we can say that f of x can be alternatively expressed as 1 over square root of 2 pi times the integral from minus infinity to infinity. And then there is a function capital F of omega. And then we have another function times I raised to the power of I omega x. And all of this is integrated with respect to omega. And this ingredient here in this expression, this function f of omega, is given as so. We have capital F of omega is 1 over square root of 2 pi times the integral from minus infinity to infinity, and then f of x times e to the minus I omega x, and this time we integrate with respect to x. And this capital F of omega is called the Fourier transform of this function f of x, that for the time being still depends on only one variable. All right? We will generalize that to the case of multivariate functions next time. Well, why would humankind, look into these kind of representations of functions? We will see next time that it is extremely handy if we want to manipulate certain properties of images, which, if you remember, we imagine to be bivariate functions, that is, functions over two variables, x and y, and well, each x and y coordinate is being assigned either a intensity value or color value. So images are functions for us. Right? But originally, when that was developed, it was not so much about manipulating properties of image functions. Rather, it was developed as a tool that simplifies the treatment of certain differential equations. And in particular, it was developed because it allows for reducing the operation of differentiation to the operation of multiplication. And we looked into that more closely last time, and this was the result we found. What we saw was that if we're given a square integrable function f of x, and we want to compute its derivative, well, of course, we may be able to do that directly. And typically we are, but sometimes we are dealing with systems of differential equations, and then things become nasty. And it would be good if there was a simpler way of doing that. And what we saw was that instead of computing the derivative d dx directly from f prime transiting to from f of x transiting to f prime directly, we could just as well compute the Fourier transform of this function f of x. Once we are given the Fourier transform version of this function, we may multiply it by the factor I omega, where I is again this unit, complex unit. And that would give us I omega times f of omega. And if we then were to compute the inverse Fourier transform, we would actually end up with the derivative. This is great, and in fact, this holds for higher order derivatives as well. In particular, if we compute the Fourier transform of the nth derivative of a function, that is indeed the same as if we were to compute the Fourier transform of the function and then multiply the result with I times omega raised to the power of n. This can be easily, maybe you can check that at home. This is straightforward. It's basically an argument based on the idea of mathematical induction. So this really is a very interesting property of this crazy mathematical expression here. It looks daunting, right? There's like square roots in there and pi's and complex exponentials and integrals and all these things. So this looks really like something non-trivial, but if we accept the fact that we can deal with these kind of things, then these kind of things simplify certain aspects of our lives. Okay, that was just, in a sense, just, have to be careful, a motivation of why it might be interesting to study this. And again, we have not yet seen why that might be of fundamental interest in the area of image processing, the area we are dealing with in this course. But we'll see next time that it really is an incredibly powerful idea for things that have to do with images. And because it's so powerful and because it's used quite frequently and well, typically nowadays it's actually hidden within the libraries you use for image processing. It's very rare that you have to actually get your hands dirty and implement these Fourier transforms yourself. But because it's so important and because it is hidden, it is actually very important that you know what it does, because otherwise you would be using these libraries without knowing like why, right? So what we are going to do is to try to understand what these transforms do mean. And that was what we began studying last time. We have started to look into where these integral expressions come from. And our starting point was the following. We had a look at the idea of periodic functions. And I said, you know, it doesn't matter if the period is some number or whatever. We can always scale a function such that it is of period 1. So without loss of generality, we assumed that we will now study periodic functions of period 1. And that is to say that we began studying functions that have the property that f of x is exactly the same value as f of x plus 1. And one way of thinking about functions like that is to express them in terms of a linear combination of sine functions. And we also throw in some constant, which I called a naught over 2, for reasons that may have become apparent if you actually verified what I told you to verify at home. So we have some constant here that allows us for an offset either above or below the x-axis. And then we have this finite sum starting at k equals 1, ranging up to some n. Have not specified that n. Some alpha k times sine 2 pi kx. This is just to make sure that the period is 1. And then we also have a phase. And the important thing to note here is that all the coefficients, all the parameters in this expression here, that is the a naught, the alpha k, the phi k, and the nu k, which is a shorthand for 2 pi k, all these ingredients here are real numbers. And I'm stressing that because, well, we saw that we may write that in a different form. So, but today I thought I should actually show you why we would be interested in linear combinations of elementary building blocks like this. And here is an example. What I have plotted here is just 3 sine waves. Right? And all I have varied is the frequency. So this is well, the sine wave where I've chosen k to be 1. If we increase the frequency by a factor of 2, we find that it will now have well, 2 valleys and 2 peaks in this interval from 0 to 1. If we increase the frequency by a factor of 3, then we have 3 peaks and valleys. These are elementary building blocks, and note that I really did not actually choose some amplitudes here or some phase angles, whatever. But still, if we, for instance, take these 3 elementary building blocks and add them together, where I guess this was 1 in all the cases here, I had whatever. Adding these things together in a linear manner, as in here, we have a sum over, I guess it was 3 in this case, produces functions like that. Right? This is, again, a function of period 1, because if we were to continue it here, it would look the same. But this is now, given that it's just a linear combination of these 3 elementary functions, it looks quite flexible. It can apparently produce a wide variety of shapes, wide variety of how it may look like. And that again depends on how we choose this, and the number n here. But we can create fairly wild things just by adding sine waves together. And to make it a bit more clear what these coefficients mean, I've shown you the effect of varying them. Again, these numbers alpha k are called amplitudes. These numbers nu k are called frequencies, and these numbers phi k are called phase. And on the right-hand side, you see what happens if, I don't know, we look at at just one sine wave, where instead of choosing alpha equals 1, which would be the blue curve, we set it to 1 over 2. We see, well, yeah, it just, changes the amplitude. Here I am changing the frequency. We have 1 peak, 1 valley, if we choose it to be 2 pi times 1. And then here we have 4 peaks and 4 valleys, so I've actually chosen that k to be 4 there. And this is the effect of varying this phi k. So by varying this number, we may sort of shift these sine waves along the x-axis. So there you have it. Apparently, by choosing different values for these parameters, we can create even wilder combinations. So it looks fairly general. What we then did was to rewrite our model of a periodic function. Again, what we started out with was this idea of expressing fairly arbitrary, fairly general periodic functions as a constant times a linear combination of sine waves. Well, the first thing we did is we got rid of the phase parameter. This was just by applying an addition theorem of sine and cosine. And the next thing we did is we rewrote this function, which at this point was expressed in terms of cosine and sine functions. We rewrote it and expressed it in terms of complex exponentials. I hope you verified that at home. And the crucial thing to note is that if we go from this representation to this representation, the summation index changes here. We are summing from 1 up to n, and with this representation in terms of complex exponentials, we have to sum from minus n to n. Right? But this is just straightforward algebra, and it is a perfectly valid representation of this idea. The strange thing is that whereas up until this point all the ingredients were real numbers, now we all of a sudden are dealing with complex numbers. These numbers ck are complex valued, and this is a complex valued function. But earlier on in this lecture we saw that the complex numbers are not really magic, they are just a way of expressing things that have more power than if we were to express things only in terms of real numbers. It's a, if you want to, a mathematical construct that seems hard to grasp, but with respect to algebraic manipulations actually can simplify our lives. And then we asked the crucial question, now is there anything to these numbers ck here? How do they look like? And of course we can, if we go from here to here, we have an expression for the ck. I hope you did that at home. But is there an alternative way of looking at them? And again, using algebra and calculus at this time, because simple algebra did not really help us any further, we found this. We found that these Fourier coefficients, ck, can be expressed as the integral from 0 to 1. Remember that we are, for the time being, focusing on functions of period 1. So integral from 0 to 1 f of x times the complex exponential function, which is given by e to the minus I, 2 pi kx, and then we integrate over x. And, well, this is a number, and it is a number, right? If we evaluate this integral here, because it's, it has boundaries of integration, we can indeed evaluate this integral, and it would give us a number, and this number is called ck. But at the same time, we may understand this integral as a function, let's call it f hat, of k. Because for different k's, we might get different results here. So instead of treating it as a number, we may also treat it as a function. And let's call this function f hat of k. Why is it called f hat of k? I didn't think of any other name. So it's just a name. And once again, the important thing to note is that this f hat of k, this integral over here, is a complex valued function. K is a natural number, minus n plus 1, and so on up till some n. It's a number, but the result of evaluating this function at k is a complex number. So the function depends on a natural number, but it produces a complex value. And we called it the kth Fourier coefficient. So here is what we have found, given our discussion up until now. We found that a square integrable function that is periodic of period 1 can be expressed, given the model we started with, as a sum where k ranges from minus n to n, and then we have this integral expression we just discussed, which is then multiplied by e to the I 2 pi kx. This thing is called 1 from now on. Now, on to new shores. Is this model general enough? Is this something we could be happy with, in the sense of now we have uncovered a way of recasting periodic functions. So we're given any periodic function, and we said, well, if there is some n we have never talked about, but say there is some such n, we can express it like this. Is that really true? Do you already know? If I ask so suggestively, then most likely not. The question we are going to address is, what about this n? What about this n? Right? Is it really enough to say that this n, some natural number, but finite, that is, I don't know, 3 trillion something something, large number, but a number, not infinity. Is it indeed sufficient to assume that this n is a finite natural number in order to express any periodic function? Any. And now we have to widen our point of view on what it means to be a periodic function. Given our discussion so far, it may seem that periodic functions are something that contains sines and cosines. Right. But that does not have to be the case. In particular, it does not have to be the case, and therefore yields the answer no. So in short, it is indeed not enough to assume this number n to be finite. Why not? Consider this. These complex exponentials we have been dealing with are nothing but a linear combination of sine and cosine, right? We have this Euler identity e to the I, whatever equals e to the I x is cosine x plus I sine x, say. These are just, these functions here are just superpositions of sine and cosine, and actually complex superpositions. But they are sine and cosine functions, okay? And sine and cosine are continuous. There are no discontinuities. They are continuous. Here is a periodic function that is not continuous. This thing is so important, it often has its own name, and because it looks like this, so this function, say, starts here and then jumps to up here, it jumps back down, it's called the rectangle function, and these things look like capital pies, and so let's just call it capital pi of x. This is obviously a periodic function. I hope you can see that. And maybe it's even of period 1, right? Because one's already, but it is not continuous. It is not, right? Obviously. And without proof, I tell you that it is impossible to represent a discontinuous function like this one in terms of a finite sum of sine and cosine, or finite sum of continuous functions. It's impossible. This is mathematics. We will not, dig so deep. It is impossible. We could say, okay, you know what? This is such a special case, we may want to exclude it. Now consider this. These complex exponentials are differentiable periodic functions. We can derive them with respect to x. The triangle function is another periodic function. This one is actually continuous, right? Because there are no jumps. It is continuous, but it is not differentiable. And we understand why it's not differentiable because we talked about this, that at certain points of these functions, the derivative from the left and from the right are not the same. So this is a periodic function which is continuous, but it is not differentiable. And again, without proof, I tell you that it is impossible to represent non-differentiable functions in terms of a finite sum of continuous functions. We cannot do that. The reasons are, again, really tricky. We will happily gloss over them. Note that this triangle in one period very much looks like the Greek letter capital lambda, so we'll call it capital lambda of x. Indeed, these two intuitions, I mean, I have not proven that, right, because this is not a math class. These two intuitions generalize further. If we assume a periodic function, this is still the case we are focusing on right now, periodic functions, we have seen they may be discontinuous We have seen that they may be continuous but not differentiable. So there might also be cases that are continuous and differentiable with respect to the first derivative, but probably not with respect to the second. Right? There might be a function out there that is continuous and 50 times differentiable, but the 51st time would produce a discontinuous function. These things exist. And indeed, if there is some higher derivative of a function we are looking at that produces a discontinuous function, then we say there is lack of smoothness in one of the higher derivatives of the function f of x we are looking at. And indeed, the sort of amount of times a function is continuously has a continuous derivative, let's say 3 times, 4 times, 70,000 times, but then it becomes discontinuous, is a measure of how smooth the function is. So in that sense, functions like sine and cosine, which we can derive infinitely many times and will always produce another sine or cosine, those are sort of the smoothest things we can think of. There are functions we can derive a couple of times and then all of a sudden they become discontinuous. In those cases, well, the arguments we just went through would apply again. If for any derivative of a function we run into the case where it is not differentiable anymore, we cannot represent it in terms of a finite sum over continuous functions. And that is to say, any discontinuity, any higher derivative of f of x prevents us from expressing this function f of x in terms of equation 1, where n was assumed to be finite. And mnemonic, like some things we might, use to remember these things, is to say that it takes very high frequencies to make edges. And here is an example of that. So, what I am showing you here is a periodic function. It's like in this trapezoid thing here. And this would continue in this direction and in this direction, but I'm just showing one period, okay, from 0 to 1. And the blue curve, well, it's not, curve, right? It is obviously not smoothly differentiable at certain points. But the blue curve is the function f of x we are interested in. And the orange curves are representations of this function f of x. I have to go back, unfortunately, I should not have done that. The orange curves are these things where I have chosen different values for n. Okay? So the blue one is this, and we try to represent it like so. And if we choose n to be 1, that is, we go from -1 to 0 to 1, we get this function. Well, if we're generous, it has sort of the same behavior as the blue thing, right? It rises and declines. Interestingly, if we choose n equal to 3, that is, we sum from -3, -2, -1, 0, 1, 2, 3, we get this orange curve, which surprisingly, or is already surprisingly close to this blue original function we're talking about. By increasing this number n to 5, we get this, and actually if we increase it to 9, we get this, and this should be a result which from your point of view is hardly distinguishable from the blue one. Is it? I mean, there are differences here and here, but this linear combination over complex exponentials is surprisingly well able to reproduce this blue function. Right? Here's a story. When I was first year student at university, I don't know about you, but we took really tough math classes, and one of the math classes was on calculus and taught by a mathematician, and we had this math book which honestly I couldn't understand. I was reading, that could have as well been written in some alien language. I had no idea what was in there. And towards the end of this math book, it was talking about Fourier series. It basically was talking about what we have been talking about last time and right now. And there were plots like this. And, that was black magic to me. How is that even possible? I mean, like, seriously, we have this crazy blue thing here, and then some linear combination over sines and cosines gives this? That was magic to me. And it still is. The crazy thing is, I am now, and this is 20 years later, I perfectly understand it. I really know why that is, and I'm trying to sort of teach you about why that is. But if I look at these, it's still magic to me. This is unbelievable. This is mathematics, right? Unbelievable. Now the good thing is, now that I started with this story when I was a stupid first semester freshman student, seriously, I didn't understand the word. And now look at me, I'm teaching it to you. There's hope. What I want to say by this is, indeed, these things usually take time. This is after some time, things become clear. And for you, the good thing is you're on the master's level already, so we can dig deeper into it, and I will do that in 2 weeks from now. But look at this. So we have been looking at this blue function f of x. Now let me magically switch the slide. Do you see a difference? So this was what we looked at right now, and now we have this. Is another blue function. Let's call it g of x because it's not the same one. And again, we try to represent it in terms of a linear combination over complex exponentials. And it is different, right? For instance, for the case where n equals 5, we have all these overshooting things here, which were hardly present for this case. Right? And now they are there. Why is that? Well, in a nutshell, without mathematical proof, it is because this edge here, this jump from here, or like this transition from here to here, is steeper than it is here. This is not as steep as this. We can say this is more of an edge than the other thing was. But again, if we go up to n equals 9, we are fairly close. We are not as close anymore as we were in the previous example, but now here is the dreaded rectangle function. And we have these overshooting behaviors here. And even in the case where n equals, and still this is magic. I mean, how is this linear combinations of sine and cosine waves able to know that there's something down here and then there's something up there? But it works, but not as good, right? Because we have these overshooting waves. In particular, these overshooting things happen close to the edge. There they are most severe. Okay. And this is what I mean when I say it takes high frequencies. So n equals 9, we have a summation over a wider range of frequencies to make sharp edges. And therefore, again, without proof, because that would take us too far afield, we deduce that to represent any periodic signal of period 1, we must consider infinite Fourier series. And there we are. Right? This is the conceptual step from last time to right now, instead of assuming some finite n, we deduce without proof, can be proven, but we don't prove it, that this has to range from minus infinity to infinity. Okay. Well, whenever we are dealing with infinite series like that, this is called a series. It's a summation over a lot of terms, very, very many terms. Whenever we are dealing with things like that, the question is, does it exist? Right? Because nobody can sit down and actually sum all the terms in this summation here. This is impossible. And the question is, are there other ways of computing these sums? And you may know that I don't know, the geometric series has indeed a closed form representation where there is no summation. Does this hold here as well? Does this exist? Can we compute this? Because practically you cannot sort of verify it by sitting down and really adding all these things together. Does this exist? Can we compute it? Or mathematically the question is, does this expression converge to some number or to infinity? If it was to converge to infinity, that would be good. Does it converge? Let's see. And again, I claim without proof, because these things are nasty, really nasty, take us too far afield. We are just interested in the application of mathematics rather than in all the dirty details. And I have to apologize to any mathematicians among us. Without proof, I claim that as long as the function we are interested in is of finite energy, which is another way of saying that it is square integrable, as long as that is the case, then we have that if we consider the difference between the function we are given, which we assume to be square integrable, and this expression in terms of sums over these Fourier coefficients times these complex exponentials, and then we integrate over this difference between the function and its approximation, and then we let this n grow towards infinity. If we do that, then this difference becomes 0, which is to say that this is the same as that, or in the limit is indistinguishable. Like it's really, is it the same? So whenever this symbol occurs somewhere in a textbook or whatever, then careful. Right? So is it really the same? Yes. It's indistinguishable. Right? But whenever we're talking about infinity, things get nasty. All right, this is our first important result for today, that it is okay for us to say that if we're given a periodic function of period 1, we can express it as an infinite linear combination over Fourier coefficients times a complex exponential. All right. And now we have to ask, why was I so happy about the Fourier coefficient? Why? I mean, instead of this, I could still have written this CK here. But last time I insisted that we find another way of writing down this CK, and this is it. And why would I ever want to express a number in terms of something freakishly difficult such as this? Who has an idea? Have we actually seen this before in this lecture series? Our question at this point is, why did I want the number ck? This square bracketed thing was called ck at some time in the last lecture. Why did I want to write it like this? Pardon? Yeah, okay, that is our long-term goal. That looks like the Fourier transform, yeah, that's true. But there is more to it, and let's look into that right now.
It's like the same formula.
Yeah, it, like structurally very similar to yes, that's for sure. But there is much more to it. So let us look into the significance of the Fourier coefficient which again is this f hat of k. It is the integral from 0 to 1 and then f of x e to the minus I 2 pi kx dx. Why would I be so keen about this function? Let me see if the blue one was. Yeah, okay, I'll switch to blue. No semantics here, it's just that it looks better. And in particular, I asked you, have we seen this before? I claim we already have seen that in our lecture number 4. What did we do in lecture number 4? We recall that first thing, we talked about the vector space ever so briefly, C over the interval AB of complex valued functions f of x over the interval a to b. Right? We talked about the notion of a vector space, and I said that in addition to these geometric vectors, let's call them, to these tuples of real numbers, the vectors we are used to, there are other vectors which form vector spaces. And in particular, I said that the set of complex valued functions over some interval forms a vector space. And I said that for these vector spaces, we can define inner products. In particular, the inner product of two functions, let's call them f of x and g of x, which are both elements in this space, can be defined, or is defined as, well, we have the inner product f of x with g of x. This is just to say that we want to multiply them in the sense of an inner product, and I said that this expression is defined as the integral from a to b f of x times g bar of x dx. Last time we saw this, it was called g star, so I don't know, g bar is the same as g star. Using bars from now on is just a different way of writing it. Is the complex conjugate of g. And now It's your time. What is the Fourier coefficient? It is an inner product. You're right. Let's be sure about this. So, I note, I'll just, point it out, like totally point it out, note that this function f of x, which we assume to be of period 1, as well as these complex exponentials e to the I 2 pi k x, are elements in this space where the a and b now becomes 0 and 1. Right? It was fairly general up to now. Now we sort of consider a special case. We assume a to be 0 and b to be 1. And therefore, this Fourier coefficient, which is the integral from 0 to 1 f of x e to the minus I 2 pi k x, not so sloppy here, 2 pi kx, whoops, x dx. This is, of course, the same as the integral from 0 to 1 f of x and then e to the I 2 pi kx complex conjugate dx. Do you see this? This minus here basically says that this is the complex conjugate of this function. But given what we just discussed, this is the same as the inner product between f of x and e to the I 2 pi kx. And this is to say, I'll write it down here. Therefore, the Fourier coefficient f hat of k is an inner product. And now you know why I wanted it to be expressed like this. Because there is meaning to that. Right? By writing it in this crazy expression, in terms of this crazy expression, we have uncovered an underlying phenomenon. Right? And let's see what this means, where this leads us. I mean, this at this point is still good and well. We now know that, there is some inner product in there. Apparently, we are dealing with some sort of a vector space, but this we should accept by now. We talked about it earlier. And now with functions, okay, they are vectors, and there's some inner product in here. But let's see what this really means. Let's see what this means in the end. And once we are through this, I hope you will appreciate what we have been discussing so far. Now, let's first have a look at the following. Note that let's consider the inner product between two complex exponential functions of the form we have been looking at so far, namely e to the I 2 pi kx, and the other one is e to the I 2 pi mx. Right. This is okay. Now we are interested in inner products between these guys, no f of x here, but two of these complex valued exponential functions here. From what we just considered, we know that we can write this as e to the I 2 pi kx times e to the minus I 2 pi mx dx. All right. Now this is a. Have to make a nicer minus here. This is the product of two exponential functions. We can express that in terms of just one exponential function. Obviously, excuse my use of the word obviously. Okay, if this is not really obvious to you, it will be in a couple of years. So we can obviously express that as the integral from 0 to 1, e to the I 2 pi x, and now k minus m dx. Okay, I just multiplied these two exponentials together. And now we are interested in what this actually gives. And this is again very important, so I will erase this and start another whiteboard. So we are about to answer the question, what is the result of integrating from 0 to 1 e to the I 2 pi x k minus m dx. It turns out, if we want to answer this, we have to distinguish two cases. And, well, first of all, we can, compute the integral, if actually really compute the indefinite integral here and then plug in the results. So let me do that. This is 1 over I 2 pi k minus m, and then times e to the I 2 pi x k minus m. This is the indefinite integral. We now have to evaluate that at 0 and 1. Okay, but this is something we have seen last time already, and I hope you verified at home that this actually gives 0. Did you? I don't know. We talked about these kind of things where there was this k minus m or plus m, I don't know. I said this is always 0. And this is easy to verify, so if you didn't do it so far, then go ahead. This is our result for the case where k is not equal to m. What is the result if k equals m? Then we have a 0 here, which is very, very bad. And we cannot divide by 0. And so therefore we distinguish the two cases, but we can do that. Because if k is equal to m, then this is 0. But then all of this is 0. So we would have that this is the same as the integral from 0 to 1 e raised to the 0 dx. And this is again something we have seen last time, when actually we did this with the Fourier coefficient, that this is nothing. This is a fancy way of writing down the number 1. If we raise something to the 0 power, this is a 1. So we have the integral from 0 to 1 dx, but this is a constant. I just did. And then we get x, which we have to evaluate at 0 and 1. And that is 1. Okay? Because we have 1 minus 0 is 1. And this is 4k equals m. So what we are dealing with here is the following: e to the I mx equals this. And now we have found that it is either 0 or 1. What does that mean? That means that these two functions are orthonormal vectors. Because if we compute their inner product, we get either 0 or 1. Which is to say, for the case k is not equal to m, they are perpendicular. And if k is equal to m, then we compute the inner product of a function with itself, and it evaluates to 1, which means that the function is of norm, this vector is of norm 1. What we see here is that these crazy things are vectors. We have agreed on that like earlier on. And we now have uncovered that they are orthonormal. And given this little computation here, we can deduce the following. And when I say we can deduce the following, this is again without going the final step, like what the mathematicians would have to do, but that would take us way too far afield. We deduce that the family of complex exponentials, and by family of complex exponentials, I refer to this set e to the I 2 pi kx. This is a function of x, but we have many of them, namely for every integer there is one such function. So this is a set of a lot of functions. Right? Those are all functions of x, but depending on our choice of k, they are different. Right? And what we just saw is that any two of them are orthonormal. And so therefore we deduce without really formal proof that this family forms an orthonormal basis of the vector space L square 0 to 1. I have further specified the vector space up until just a few seconds ago. I talked about the vector space of complex valued functions over this interval. Now I'm already narrowing it further down to the vector space of square integrable complex valued functions over this interval. All right? But earlier on, we discussed the idea of vector spaces, and we saw that that is a notion that is much more general than what we may have learned up until so far. Then we discussed transformations of vectors. And when we discuss these kinds of transformations, and we'll look into that more closely in a second, we saw that we can express vectors in terms of linear combinations over basis vectors. Then we started looking into what it means to be a Fourier transform, and we did so by focusing on the special case of periodic functions, and we uncovered this crazy Fourier coefficient, for which we now just established that it is an inner product. It is an inner product between vectors of a form we may not be quite so used to than the vectors we are very familiar with, but those are vectors, and they have an inner product, and we saw the Fourier coefficient is an inner product. And what we now saw, that one of the factors in this inner product is a basis vector. right? Because on the previous slide we established that these things which occur in the Fourier coefficient are orthonormal. So we are now talking about functions which form a vector space, and we have uncovered a set of basis vectors for this vector space. Now then, it's quite natural to take the next step and really make sense of what we have learned so far. So, because of all of this, we have, therefore, the Fourier series, that is our way of writing any such periodic function in terms of a sum where k ranges from minus infinity to infinity, and then we had f hat of k times e to the I 2 pi kx is nothing but a sum where k ranges from minus infinity to infinity, and then we have an inner product f of x e to the I 2 pi kx e to the I 2 pi kx. Right? And we now recognize that this Fourier series we spent quite some time on developing is a way of expressing this function or vector f of x in terms of the basis. The basis provided by the complex exponentials. This is a linear combination. These things are basis vectors. We have coefficients here times a basis vector, and we add that for a lot of coefficients and a lot of basis vectors, and we get something. This something is a vector, and we have uncovered that this Fourier series is a way of writing this vector in terms of a basis we may have never seen before. Who has seen this basis before? Okay, now you know it, right? There you go. And to really point it out, I will make the connection to the kind of vectors we are used to, okay? So, for the mathematicians, take your heart pills. Because, you know, I'll get back to this later. This is and now here's a fancy term, Hilbert space, generalization of the, well, familiar, and I say familiar because we have been looking into 2D cases, familiar 2D case where, let's say, we're given some vector x that is a collection of two numbers x1 and x2. Where for this vector x we have we have that this vector x is the same as a coefficient x1 times a basis vector e1, let's assume it's the standard basis vector, plus a coefficient x2 times a basis vector e2. Now where do these coefficients come from? So we have, I don't know, some x here, and we have the standard basis. And of course we know that the x1 coordinate is the inner product of this vector with the vector e1. So this is the same as the inner product of x and e1 times e1 plus the inner product of, make it like this, e1 times plus the inner product of x and e2 times e2. And the reason why I have written it in terms of x1s and 2s and e1s and 2s instead of x's and y's and x heads and y heads is, with this notation we can simplify this to the sum where in our case I ranges from 1 up to 2, very high dimensional, x ei times ei. And can you see that this is the same as the Fourier series we just discussed? The crucial difference is that this is a very finite sum, right? Even if these are n-dimensional vectors and this n can be very large, this is always a finite sum. And the crazy, crazy difference is that for the Fourier series, this sum was infinite. And because of the infiniteness of this sum, I said it is a Hilbert space generalization of this. You have taken your hard pills. Hilbert spaces are vector spaces of infinite dimension. Let's keep it at that. They are very special. They are very special because, well, I said, we have these functions and they are continuous. And so, in contrast to these discrete vectors here, these functions are in a sense sort of continuous, so they have lots of components. We'll get back to that. Lots of components. They are sort of continuous objects living in infinite dimensional vector spaces. We'll get back to that later. And again, we're talking about infinity. This thing occurs, and I already said, like whenever that occurs in any of your books or whatever, you have to be careful. So when I say Hilbert space generalization, this is indeed, like the Fourier series is indeed a generalization of this, but we have to be extremely careful with taking this analogy too far, right? It is definitely enough for our purpose. We are not mathematicians, we don't have to dig really, really deep into that. What, and this is the last thing I do here. I'll just do it again. So we have derived so far that a function f of x can be expressed as a sum that ranges from minus infinity to infinity, and then an inner product f of x with a vector e to the I 2 pi kx times e to the I 2 pi kx. So this is indeed exactly the same structure as this. Right? What is different here is the number of terms. This is very, very finite, even if n is 50 billion. This is like nothing against compared to infinity. This is a totally different beast. And what is different is that for these, say, geometric vector spaces, we can easily picture the notion of basis vectors and so on, so even if it's high dimension. And here we are dealing with a vector space that too has basis vectors. These basis vectors are, again, different beasts than these ones. But the Fourier series we have uncovered is something we are used to. It generalizes something we are used to. All right. Yeah. Okay, let's see how far we can take it. I'll speed up a bit. I spent a lot of time on this because it is important to me that you can make sense of this idea of a Fourier transform. And you all are familiar with vectors and how to express them, and now we are talking about different vectors, but we express them in ways we are used to. And I try to wrap this up because in the end we are interested in applications of this. So that is actually what I was planning for the next time. Let's see how far we can go. We have been talking about Fourier series so far and not about Fourier transforms. That is, whatever we have learned so far has to be generalized a bit further. And that is now we look into the idea of transiting or transition to the Fourier transform. Right? So far, periodic functions of period 1, summations instead of integrals. And the Fourier transform we saw on the slides earlier on today involved integrals. Where do they come from? And I cannot stress this enough at this point. I stressed it a couple of times already, but now it really applies without rigor. So what I am going to do now is, well, kindergarten mathematics. Well, it of course is not, right? It is master level mathematics for computer scientists, but mathematicians would drop dead by what is to follow. Everything I'm going to do right now can be done rigorously. And it has been done rigorously, and we know that the end result is true. We cannot do it on this low level. All right? So I'll just ever so briefly provide you with an intuition where this comes from. But without rigor, and in particular, I will not ask you to verify anything at home right now. But there's actually one thing I've asked you, but yeah. Let's just accept it. What we are going to do is we are going to transit from periodic to non-periodic functions. Right? This is a question we could ask. Why would we focus on periodic functions anyway? And the way we are going to do this, the idea we apply is to view non-periodic functions as the limiting case of periodic functions. Periodic ones. And that is to say, we consider a period of t, some number t, not 1, and then we let this t become very large. And there is this dreaded symbol again. And let me do this quickly. so that we can wrap this up to And once more, whenever this thing occurs, you know that you have to do some deep thinking. And we don't have the time for that. And we actually don't want to. So, if this f of x is periodic with period t, capital T, the Fourier series becomes, I'll just write it down, f of x is the sum where k ranges from minus infinity to infinity, f hat of k times e to the I 2 pi k, all of this is divided by t times x. This is just this scaling we discussed last time. And the Fourier coefficient, becomes f hat of k is 1 over capital T times the integral from 0 to t e to the minus I 2 pi k over t times x f of x dx. And this is the same, and this is what I want you to verify at home, 1 over t. Now we integrate from t over 2, minus t over 2 to t over 2. From minus t over 2 to t over 2, e to the minus I 2 pi k over t x f of x dx. And I want you to verify this at home. Verify at home. Right, that it is indeed, it doesn't matter if we integrate from 0 to t or from minus t over 2 to t over 2, if the period is t. Okay, check this out. Why do we need this 1 over t in front of here? Right, this is something that wasn't there earlier. So why do we have this factor 1 over t? This is because this is because if we compute the integral from 0 to t of this expression e to the I 2 pi k x, this again is divided by t, times e to the minus I 2 pi k over t x dx, that is, if we compute the inner product of these basis functions with respect to a different period now, this is not period 1 but period t, we compute this inner product where again like k is now assumed to the same thing. We saw that this was 1 a bit earlier. Now this would be t. And this is something we don't like. Right? We want these things to be unit vectors, and so therefore we use this. Right? So therefore, this is just a normalization. Can you skip that? Oh, we're good. I guess we can do that. Okay, now let me introduce a new friend. That is 2 pi k over t, blah blah. This is, I don't want to write that anymore. And we define, and actually we're not the first to do so, this has been done in physics like 300 years ago, the notion of an angular frequency, and this is just to say that there is something we shall call omega. We have seen this guy before, and we use it to sort of abbreviate this. So omega is from now on 2 pi times k over capital T. This is, of course, the same, or this is to say that k is omega times capital T over 2 pi, algebra. And now some calculus. We know. And I'm pointing it out. Here is where my exposition becomes sloppy, but intuitively understandable. This k here has been so far, or is still, those are integer numbers, right? Minus 50 million something, minus 50 million something, plus 1, all the way. No, those are integer numbers. They are integer numbers. The difference between two such k, that's sloppily, dk. This is not, I mean, this really is not an infinitesimal object, but dk is 1. Okay? At least, they are 1 apart. And we can think of this, if this t becomes very, very large, then this will ever so closely approximate any arbitrary real number, and this becomes really large, goes to infinity. This is not a rational number anymore, and becomes, more like a real number. So for this omega, we can look at infinitesimals. There we would have that the omega, I just do it here, is 2 pi over t, those are constants, times dk. And I just said, and again, like hard pills, dk is 1. So this is to say that dk is t times d omega over 2 pi times 1. Well, this is 1. This is 1. That was what I said. Is 1. Now with this new thing here, with this omega, I will now define a new function, but this is just plugging in stuff. Then, let us consider this, let's say f tilde. It was a head previously, now it's a tilde, and it did depend on k previously. Now we make it a function of omega. Is 1 over t times the integral from minus t over 2 to t over 2 f of x e to the minus I omega x dx. That is acceptable, right? No k there anymore. Every k has been replaced by an omega to make sure that this is a different function, not a function of k, but a function that uses tilde instead of a head. But this is what the Fourier coefficient used to be. Okay, if that is another way of writing the Fourier coefficient, then how to write the Fourier series? Well, we write it like f is the sum where omega t over 2 pi ranges from minus infinity to infinity. Note that I have replaced the k by something else. And then we have e to the I omega x times f tilde of omega. Now, hard pills. This is the beauty of mathematics, is you can do it on different levels. I remember how shocked I was when I learned physics at university and compared it to the physics I learned at high school. It was the same thing, but more correct. That is to say, what I was learning in high school was not wrong, but it was doing physics on a kindergarten level compared to what we were doing in university. It was the same thing. The stuff at university was more correct, and here's another instance of that. We, again, once more, and I'm never saying it again, could do all this, like, you know, really, really, really seriously, like mathematicians would, but we are not. To us, it's more important to see how these things, where they come from, to be courageous enough to work with them from now on, right? So we don't need all the details, but I can still, without all the details, make it, present it such that you can appreciate it. Now, this here is the same as if I were to multiply a1, right? There's nothing to it. And actually, mathematicians love to consider very complex ways of writing down a1. And we just met one of these things. If I rewrite this one in a different form, so we have this sum where omega t ranges from omega t over 2 pi from minus infinity to infinity, e to the I omega x f tilde of omega, and now comes the 1, t over 2 pi d omega. It's a1. It's a1. And note that this t here will cancel with that t. Right? In this f tilde thingy here, there is a 1 over t, and this will go away with this t here. This is cool. But there's still a t in here in the summation index. And this we will now let become very, very large. And so what I'm saying is now then we let this go to infinity. Then what I just erased can be written as f of x 1 over 2 pi integral from minus infinity to infinity times the integral from minus infinity to infinity f of x e to the minus pi omega x dx, and that times e to the I omega x d omega. This is, yeah, that can be made precise. I'm not doing it. I just say if this grows, then this is what we get. There is an equation sign missing here. So f of x is 1 over 2 pi. We saw where this 2 pi comes from, right? It was contained in the funny 1. Yeah, and then I'll write this 1 over 2 pi in a slightly different manner. 1 over square root of 2 pi times the integral from minus infinity to infinity times 1 over square root of 2 pi integral from minus infinity to infinity f of x e to the minus I omega x dx, and all of this times e to the I omega x d omega. There we are. There we are. I will erase this once more and sort of write down our final result. Note that by these really coarse hand-wavy things, we have uncovered that what was the Fourier series up until a few minutes ago is now an integral, right? And this integral is had a factor of 1 over 2 pi, which I can write like this, right? It doesn't really, if I multiply this, but we can pull this out, whatever. This creates symmetry. You can write this 1 over 2 pi in terms of 2 square roots of 2 pi, right? And this integral contains another integral. This one we have been working with earlier. This is nothing special here. It does not involve k's anymore. It's now expressed in terms of angular frequencies, omega. So let's pull these two things apart once again, and then we are done. In particular, all we are going to do is now to define this here to be a function capital F of omega. That's all, right? So what we find is, or we define the Fourier transform of the function f of x. I'm skipping those details now. Is 1 over square root of 2 pi times the integral from minus infinity to infinity f of x e to the minus I omega x dx. But this is a definition. And the inverse Fourier transform is f of x is 1 over square root of 2 pi times the integral from minus infinity to infinity f of omega e to the I omega x d omega. There we go. So this was rough, and this is just, it is just to motivate that, yes, indeed, these two results can be produced. We can produce them, like, seriously. Now, today we spent quite some time on understanding the Fourier series, which is now generalized to what we call the inverse Fourier transform, where we express a function in terms of its Fourier transform. But look at this, where we had a summation before, we now have an integral. There was a summation over k, and that went from minus infinity to infinity. And then there was this Fourier coefficient, which we now call the Fourier transform, times the complex exponential. Now, for these complex exponentials, just as we did with these discrete ones, where we had a k, 2 pi k in there, you can easily prove that any two of them are orthonormal. That is, if you compute the inner product of this function with another function where the omega is I don't know, some lambda or whatever, then this will be 0. However, if you compute the inner product of this one with itself, it is 1. So this is yet another generalization from an infinite summation to an integration. And this is now a true Hilbert space, right? This is now a continuous, like we have basis functions here. How to picture them? Points on the unit circle, whatever. These are basis functions. And this here is still an inner product, right? Because now the a and the b is minus infinity and infinity, but this is still of the form of what we called an inner product of complex valued functions defined over some interval. This interval is now the largest possible interval we can think of, but it has the form of an inner product. So, in a nutshell, the Fourier transform is indeed just a projection. It's an inner product. It projects a vector we are given. This vector is a function, and it's becoming tedious to talk about functions and vectors simultaneously, but it projects a vector into a certain system of basis coordinates. And once we have these projections, we can recreate the function by multiplying their projections along these basis functions with the basis functions. Then we get the function back. That is all there is to it. And I will, next week, I guess, or the week after next week, come back to that, and then we really dig a bit deeper, because this is tremendously, it's tremendous fun. What we are going to do next time is take a leap of faith, and you will hopefully believe me that we can do all of this. Now it was done with respect to functions of one variable, can also be done with respect to functions of several variables, let's say x or y, which takes us back to the case of images, and then we'll study applications of this in the case of context of image processing. And we'll learn about how this relates to the idea of linear filtering, and then we'll come back to this and really understand this. Right? In particular, one question you should ask yourself already at this point is, well, if we can express this function in terms of this basis, and this is not the way, if you're talking about, say, function, I don't know, sine of x, you are typically not talking about this function as 1 over 2 pi, blah, 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 blah. You are talking about sine of x. But if sine of x is nothing but a vector, which can also be expressed like this, then what is the standard basis you're usually assuming there to be? This is what we will be looking into next week. All right, that's everything for today. Are there any questions? If not, then see you on Thursday.